Okay, so this is a problem about Lewis structure of C2F2 and understanding the hybridization on the carbon in C2F2. So the Lewis structure starting from as C2F2 is the count number of valence electrons there. So carbon has 4, there are 2 carbons, and the fluorine has 7, there are 2 of them. So this is 8, that's 14, that makes 22 valence electrons, right? So you have 22 valence electrons to draw. And then where do I put these compounds? And then let's say, let me see if I can put carbon in the middle and fluoride on the outside. And we can think about forming carbon-carbon bond and carbon-fluoride bond. So to make this one as a molecule by default, you should have 3 bonds to connect those atoms together. So to begin with, you have 22 electrons, valence electrons, and how many you have used to form these 3 bonds? 3 bonds means 6 electrons, right? So you use 6 of them, and then now you ended up having 16 electrons. And one thing that nice tip to think about the Lewis structure containing this halide, something that halogen, fluorine, chlorine, bromine attached to it is, their subunit of Lewis structure is more likely shown in this form. So remember this, okay? So remember that as a way. So the fluoride will likely form 3 lone pairs, and in this case, the next step that I can use to draw the Lewis structure is those 3 lone pairs on both sides, and each one of them use a 6. So I have used 12 electrons form of the lone pairs on the fluoride. So if I do that, I will have 4 electrons left. So then what do I do with these 4 electrons? And if I start to number up understanding the octet rule, this carbon has 4 electrons so far. Feel like it. This one has 2 bonds, so they have 4 electrons so far, counting these covalent bonds and as an electron. So they are in short of 4 electrons, and you only have 4 electrons on both sides. The only way that you can essentially have to use this electron is by sharing those electrons together. So if I use this one as a different color, so okay, I have 4 electrons to do, and the only way this carbon in the middle can feel like having 4 electrons is you are going to put 4 electrons in this way, right? So you then this one feel like having 8 electrons, and then you fulfill the octet rule. So does this one, 8 feel like having 4 electrons. So this is a case that the final picture that gives us important clue on the Lewis structure, and therefore my Lewis structure at the end is, okay, carbon will form triple bond with carbon with fluoride and attached to the both sides, and this is 3 lone pairs. There's a halide bond formation. So that's the Lewis structure. And then now the question is hybridization of carbon. So this one, we are only count the number of sigma bond. There is 1 sigma bond. I would say there is another one. There are 2 sigma bonds in the lone pair. So 2. 2 corresponding to SP or SP1, where people actually say SP, right? So that's the hybridization for the carbon. So in the case of here, the answer is A, sp hybrid orbital. Okay, so this problem set question number 8 and 9 in exam 2 is dealing with what we call the molecular orbital and understanding what we call the bond order. Okay, so when you have a diatomic species and 2 atoms are bonded together, and we have to figure out what is a bond order and how strong they are bonded together, and we are using this bond order and then this is coming from the essentially MO, molecular orbital theory. And if you're looking at the diagram provided, and if you look at this bottom, the fine print here, and it's the boron, carbon, and the nitrogen, which is shown up as a lighter element. And when they form this diatomic molecule, they essentially following this energy diagram shown up on the left. For the oxygen, fluorine, and the neon, they are essentially, which is heavier atom, and in that case, they are showing the diagram on the right. And if you look at closely, this is a sigma star, and the sigma, and then this is a pi. So sigma and pi, sigma and pi. So the one that without superscript star means a bonding orbital, and this one, the one with this, the star, which is this one is a pi star, sigma star. These are the anti-bonding, right? So this is mean the anti-bonding, and this is essentially bonding electrons. So the formula that I'm going to use is bond orbital is half of number of electron in bonding orbital minus number of electrons in anti-bonding. So this is a bond order equation that I'm going to use. And so let's see how I can figure out this problem number 8. And if you're looking at the problem 8, it's either fluorine or neon or oxygen base. They are all shown up here. So therefore, I'm going to use the diagram shown up on the right. In this case, they're going to have sigma star. So this is coming from the 2s, and then there is another sigma and pi. There are 2 pi's, and so this is coming from the 2p orbital, and they can form sigma bonding, and they can form 2 pi bonding, and then there are pi star, which is the sort of the opposite side, or sigma star. Okay, so this is the energy goes up, so you're going to fill up the electron following this way. And then I need to figure out how many electrons are available in each case scenario, and let's look at the case in here. So fluorine and F2, in that cases, you are going to have the fluorine have where is it? Okay, there's a 7, right? 7. There are 2 of them. So you have 14 electrons. And the 14 electrons, and I'm going to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so because of that, I have the bond order for F2 is a half of, how many do I have? I have 2 here, and 2 and 4. So overall I have 8 electron in bond orbital. And how many do I have in the other side, which is showing up? This is an anti-bonding, there's an anti-bonding. I have 2, and I have 4 more. So I have 6, so minus 6. So in this case, my bond order is 1. So in this cases, your bond order is 1. What about if you have a F2 2 plus? Okay, F2 2 plus. This means how many electrons? You will have 14 electrons for the neutral case, and the 2 positive charge means 2 less electrons. You have 12 electrons. Okay, so 12 electron means if you're looking at the diagram, the last 2 electrons are not being filled up. So the bond order here is, if you count the 12 electrons from the bottom to the top, you'll find out 8 in the sigma and the pi bond orbital, and then there is there are 2, and then there is a 2 in the pi star, so there will be 4. Overall, you have a 2 bond order. So this one has a higher bond order than the one shown up in the case of A. Okay, so neon, which is now the neon, and neon is the 2 plus. So what that means is neon is shown up here, which is there is a noble gas, which is 8. So there are 8 valence electron, but you develop 2 charge plus 2 charges, you lose 2 electrons, so overall 14 electron. This is the same case as case for the F2, and your bond order is essentially same, which is your bond order is 1. So this is the bond order 1. And what about O2? Okay, so O2, 2 plus. So oxygen, there are 2 of them. Oxygen has a 6 valence electron, and then you are losing 2 electrons to develop positive 2, so minus 2. So overall, you will case of an oxygen, you will have 10 valence electrons to fill up. Let me use a diagram shown up here. And so, okay, I have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the bond order here is, if I count this, I have 2 here, 2 here, 4. The overall, I have same again, the 8 electron in the bonded orbital, whereas the case for the anti-bonding, where is it? Yeah, there's an anti-bonding. I have a 2 in the anti-bonding and nothing else. So I have 2. So that means the bond order here is the case for the 3. So this is the case for you have a bond order of 3. Okay. The last one is F2. Okay. So F2 2 minus. So F2 neutral is a 14, so the 14 plus, there are 2 more electrons, so you have a 16 electron in total. And if I have a sigma, sigma star, sigma pi, pi star, sigma star, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in this case, you have filled up everything, and the bond order for this F2 2 minus is half of, you have 8 electrons in the bond orbital, you have actually 8 electrons in anti-bonding, so it's actually bond order 0. And that means is that they do not exist, and they cannot form the bonding. In the point of bond order is a 0. So the one with the highest bond order is, I get bond order of 3, which is a number D. So that's the answer. Okay, so here is another question. So about using this is question number 9. So using the question 8 and 9, you are using this molecular orbital diagram. And in this problem 9, they're asking which one is most stable. Does this diatomic molecule have a most stable bonding? And this is the same wording as the one with highest bond order. Okay? Which one formed the most strongest bonding, and that must be the stable diatomic molecule. And now you see this, all the compound that you see is carbon, nitrogen, boron is fall into this category. So I'm not going to use this one, but I'm going to use the diagram shown up here, because because these are the lighter elements, and then their energy sequence is essentially sigma, sigma star, pi, sigma, pi star, sigma star. So sigma, sigma star, pi, sigma, pi star, sigma star. Okay, so these are the bond energy level rank of molecular orbital in this lighter element of diatomic molecule. So what we need is essentially count the number of once again the bond order once again is half of number of electron in the bond orbital minus number of electron in anti-bonding orbital. Okay, so this is something that I need to keep track of. And for the case of carbon, carbon has what? 4 electrons in valence electron. I have 2 of them, so there are 8 in as a neutral. And then I need to develop positive 2 charges, so I need to lose 2 electrons. So then makes it, this one has 6 electrons. Okay, 6 electrons, and I'm going to draw this case where 1 sigma, sigma star, pi, sigma, pi star, sigma star. Okay, and then the sigma, sigma star, pi, sigma. Okay, and the pi star, sigma star, because this is a diatomic molecule of the lighter atoms. Okay, and then I'm going to fill it up. 1, 2, 3, 4, 5, and 6. So this, by doing it, my bond order for this case is BO half of, I have 1, 2, 3, 4, 4 electron in the bond orbital, and there are 2 in anti-bonding orbital. So therefore, this is a bond order of 1. So this is a bond order of 1. BO is 1 here. For the nitrogen, which is 5 valence electrons, so you have a 2, 5, which is a 10 electrons, and you need to lose 2, so that makes it 8 electrons. So if you're looking at this diagram shown up, I need to use 2 more electrons. Okay, so the 2 more electrons, so where does it go? It goes up here, this one and the bottom one. So therefore, your number of bond orbital, number of bonded electron is actually goes up to 6, and the one in the anti-bonding is still 2. So you are going to have bond order of 2. So this is a bond order of 2. Great. Okay, so it's going up. What about the boron? So boron is actually the group 3, right? So you have a 2 times 3, and it's a neutral, and that's it. So what do you have? 6 electron. So 6 electron is same case of carbon to 2 plus. So this is a bond order still 1. What about the carbon to 2 minus? Okay, so in that case, you have a 4 electron from carbon. There are 2 of them, and there are 2 extra electrons, make it 2 minus. So you need 2 more electrons, so that make it 10 electron in total, right? So let me use a diagram for here. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is how you're using it. So bond order for this C2 2 minus is you have 2, 4, 2. So you have 8 electron in the bond orbital, and there are 2 electron in the anti-bonding orbital. So in that case you have bond order of 3. So this is a case of BO is 3. And finally B2 2 plus. So boron is a 3, so there's a 2 times 3, that's a 6, and you're losing 2 electrons to develop 2 plus, so minus 2 electrons. You have, how many electrons you have? You have a 4. You have 4 electrons. Okay, so to have a 4 electrons, essentially you fill it up. You see essentially this is a 1, 2, 3, 4. So it's actually you have a sigma and the sigma star, and that's it. So actually your bond order here is cancel out. 2 minus 2 is 0, so your bond order is 0. So actually this molecule do not exist even as a bonded molecule, because bond order is 0. So at any rate, most stable molecule highest bond order in this case is bond order of 3, which is a case D is the answer for this one.